This episode is all about friction.
Yeah, friction!
Keeping things suspended up high thanks to friction, like this. And this. And even me.
Okay.
Climbing. Sliding. Lifting. And falling. Falling? I guess not yet. All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil, and today we're talking about friction. I didn't slide.
Take two.
I can't, I'm still not. Oh, I know. I got it.
Take three.
Oh, socks don't work any better.
Take 15. 34. Take 36.
I don't know why I thought that would work.
Take 52.
I'm Phil, and today we're talking about friction! Sorry, okay. Oh, friction! We did it! We got it, everybody! How many takes was that? Oh. Well, still, we got it. Good work. As you may have already guessed, today is about friction, and here's a really easy friction experiment you can do at home. All you need is a piece of wood. You don't need the frame, and you don't have to do anything fancy to it. Just put one end up on a couch or a coffee table and make a nice ramp. Then you want something to slide down that ramp, and I like to use a piece of wood. Now check it out. Wood ramp, wood block. The friction is so much that the wood slides to there. Now what I like to do is take a little flag and mark the results. Recording the results is good science. Now here's where it gets fun. Get another surface and attach it to the wood, like carpet and wood. Let's see how far this goes. Not as good. All right, record the results. Cardboard. Ooh, nicely done, cardboard. Foam. And this wood has been waxed, like on a floor wax, which makes it nice and slippery. Let's see how that does. Ooh. And now the ultimate ice attached to wood. This is actually harder to do than I thought. All right, let's try it out. Ice! The clear winner. Not a big surprise right there. And get this, once you've done all of that, you can change the surface of the ramp. You can go to waxed wood, carpet, foam, cardboard. Well, yeah, you get the idea. Record all the results, compare them, and there you go. Friction ramp experiment. And that's what we're gonna be maxing out today. So come on, let's go. Check it out, I've improved the portal interface. Watch this. Yeah, and then I can scroll through experts, and oh, this is gonna be fun. And I've got my coordinates right there. Whoa. That's never happened. Okay. Hey, Sarah!
Hey, good to see you again.
Good to see you too, Sarah. From Mad Science, you're gonna help me max out friction.
Yeah, friction.
What do you think of my max out friction room?
It's amazing. It's so wonderful. So how are we gonna max out friction today?
In the lab, I had a ramp and I had stuff with different surfaces on it.
Oh, that's so cool. It's too bad you don't have it here. We could totally test that out.
I can bring it here.
Awesome.
I have a new app on my phone that talks to the portal. And let's see. That's not what I... Oh, hold on. Okay, there we go. And... Whoa. Well, I can do this. It needs an update.
Yeah.
That's what the... Yeah!
There we go.
It is. Okay.
Perfect.
So here we go.
Amazing.
The friction ramp, it's pretty simple. You just take, I've got blocks of wood with different surfaces.
Amazing.
And then you just slide them down the ramp.
Right. So cool.
Yeah, so what if, to max it out, what if this is us?
We're a block of wood?
No, I mean like we are on the block of wood and then we can try changing the bottom. I guess a block of wood isn't the right thing to use, though.
Right, yeah. Maybe we could use like a sled.
Oh, yeah, okay, like a snow sled. That's a great idea. Okay, so we'll tell you what. I will portal in a sled for
Are you
us.
sure you want to portal it in?
I'm sure. Just stand back,
Okay.
though. Okay. Ha!
Ah, there we go.
Maxed out friction slide! You ready, Sarah?
Yeah, I'm ready.
Okay, here we go.
All right.
Sarah and I pushed each other around on the sled, which was fun, but it was also tiring.
It's pretty hard. This is my turn. My turn.
All right.
Oh, yeah! Whoa, friction! Yeah, friction! Yeah! Yeah, friction!
But we soon realized it'd be pretty hard to measure how much friction there was.
You know how hard you were pushing?
I had no idea how hard I was pushing.
A lot, but that doesn't really help in science terms. So
Exactly.
what do we do?
Well, with your first experiment, you used a ramp. Could we maybe put a ramp up in here?
In here?
In here, yeah.
I guess.
Then we can measure also how far we go so we know how much friction is being used.
Right, so we have our control, and then we have all the, just like the blocks.
Exactly, just like the block.
Okay, great. So we'll get the ramp, we'll get a bunch of wood,
Right, yes.
we'll get some tools.
Yeah.
The case of the missing friction! It was rough all over in the big city. My toughest case yet, and I felt like I was getting nowhere. Someone stole all the city's friction. And it was my job to find out who and get it back. But after a week, I was no closer to solving the case. It was hard to get anything done now that there was no friction. Uptown to downtown, people were sliding all over with no way to stop themselves. It was chaos. Chaos, I tell you. But if there was any detective that could solve the case, it was me. But it's like my grandma always said, it's tough to follow leads if you can't sit in your chair. Nothing stays put in a city without friction. And you never appreciate something till it's gone. The phone rang. Sure, I wanted to answer it, but it slipped through my grasp just like this case. The mayor was on the line. He wanted to know if I'd made any progress. But I felt I was going in circles.
I'm gonna have to call you back, Mr. Mayor.
Without friction, you couldn't do very much at all. It was going to be my toughest case yet.
Sounds good.
Sarah and I are maxing out a friction ramp. Step 1, make a giant ramp.
There, are we done?
Great, I think so.
We're done. But it proved a bit hard to lift up to the second floor. Fortunately, Sarah had an idea.
Maybe we could use this crane.
We use the crane! Oh, yeah, I've got a 5-ton crane at Science Max headquarters. Good thinking, Sarah.
So we rigged it up and tried it out. The bonus was we could make the ramp any angle we wanted.
Okay, time to get my helmet, because don't go any higher than that, because I don't have my helmet. And then we will start sliding down.
All
Friction
right,
ramp!
friction.
I got on the slide and Sarah lifted it up until I started moving.
Ah! Friction ramp!
And that allowed us to record our results.
We're at 2 meters.
2 meters!
meters.
Recorded! First recording done,
All
now we
right.
switch it up.
We tried it again with Sarah on the slide to see if she slid at the same height. And she did.
Yeah.
Now we have a way to record the results. The plastic sled went down the ramp at this height. Things with more friction will mean the mark is higher, and less friction will mean the mark is lower. So then, we tried it with...
Cardboard! Cardboard! What did we get?
And it was...
A little over 2 meters.
meaning...
Cardboard is a little bit less slippy than the plastic of the sled.
All right.
Ready for carpet sled?
Good to go.
Here we go. Oh, past 2 meters. Oh, almost 3.
Here we go.
Carpet had even more.
Oh my gosh, we're going this side.
Whoa!
That was so cool.
That was exactly 3.
Then we tried foam.
Coming up on 2 meters. All right, coming up to 3.
And just like the wood block, the foam didn't slide at all.
What if I like do this and then I slide? Right, so, friction sled on foam, highest friction of all of the materials. Oh, hello there. Here's a fun science experiment you can do with science and friction together. Take two books, put them on top of each other, and pull them apart. Ooh, not too much friction. But if you take the books and you interleave some of the pages, maybe 3 or 4 parts, and try it again, pull them apart, they're a little harder to pull apart. That's because the friction for more pages touching each other actually starts to add up. So, what if we were to take 2 books with a lot of pages and very carefully and meticulously take each page individually, one at a time, and overlay each one and go back and forth? These are 2 books completely shuffled together. The elastic band is actually just to hold the covers together. All right. So, now the friction between all of these pages, when I try to pull it apart, makes it pretty much impossible. Now, there's 2 things going on here. First of all, when you start to pull the books apart, the pages start to stick together because they squeeze together, because you're pulling and they're squeezing. And the fact that there's so many pages sticking together, the friction builds up to a degree that is actually very impressive. But don't take my word for it, let's max it out. Here is another 2 books, elastic just to hold the covers. This one clamped to the wall, and I'm gonna pull on this one. Science! Still don't believe me? Well, let's max it out some more. 2 books, all the pages layered together, held together only by friction suspended over a giant vat of slime. Now, let's see how much faith I have in science. Friction! Yeah! Okay. Okay, oh no. Okay, now to get down. Okay, hold on. And then. Science! That was close.
Sarah and I have used our maxed out friction ramp and compared the regular sled to cardboard and foam. What's next?
We've waxed the bottom of this sled, and we're gonna try a wax sled next.
Wax sled!
All right, here we go. All right.
1 meter.
Oh boy.
1.5 meters.
Whoa!
Wax sled! Woo! The slipperiest yet, only
Yeah.
1.5 meters.
That's awesome. Do you have anything that's more slippery?
Yeah, we do. We have ice sled. Are you ready to try it out?
So ready to try it out.
Okay, let's do it.
All right.
And
There we go. Whoa! That was awesome.
look how far you went.
That was so cool.
And only 1.25 meters.
Least amount of friction.
Ice wins. So I think we should do something else to max this out, though.
Maybe bringing it up a little bit more and
Yeah.
using something with less friction.
Wait, I have an idea. Yeah, okay, come with me. This is a climbing frog. Why does he climb? Because of science. I pull on this rope, and then I pull on that rope, and I pull on that rope, and that rope, and he climbs up the ropes. And why? Well, because of friction. The secret is 2 straws.
The straws are pointed away from each other at the bottom. This allows it to climb thanks to friction. Take a closer look. When I pull on one string, it pulls straight, which makes the frog pivot. That string slips through the straw because there's not a lot of friction, but there's lots of friction on the other side because of the angle. So one side of the string goes down, which makes the other go up, which means the frog goes up with it. All thanks to friction.
So now, let's max it out. This is a super maxed out climbing frog.
Just like the small version, I have a rope going through 2 tubes. I pull on one rope and the other holds on by friction. Then I switch.
And it does work. It's just a lot harder to pull on the ropes, but it totally works. Whoa, whoa. There, and then this one, and then that one, and then that one. Yeah! A giant climbing frog! All because of friction. Here's another way to defy gravity using friction. Get a plastic water bottle and fill it with rice.
Take 2.
So get a plastic water bottle and fill it with rice using a funnel. Then take a shish kebab skewer and stick it into the bottle and nothing happens. But if you tap the bottle down, the rice starts to pack in a little bit better. See how the level of rice is lower? Which means you can add more rice. Pack it down even more. And you can even use something the same diameter as the mouth of the bottle, like, say, a highlighter. And make sure all the rice is as packed in as you can get it. There. Now the rice is really packed in there. And when I stick the shish kebab skewer in, the friction between the pieces of rice and this wood is enough to lift the bottle using nothing but friction. Now, let's max it out. I filled this 20-liter water cooler jug full of rice, and it's really heavy. I wanted to see if I could lift it using nothing but friction and this dowel, which is just a round piece of wood. All right, here we go. Ah, science! I'd max it out even more, but I don't think I could lift anymore. It's okay, I could just fit.
Newton's first law in 60 seconds.
Newton's first law says an object in motion tends to stay in motion. So why don't they? See, if I was to throw this, it doesn't stay in motion, it doesn't keep going, it slows down and falls to the ground. Well, the whole law states an object in motion tends to stay in motion until an external force acts upon it. So what forces are acting upon this? Well, gravity for one, pulling it down towards the ground, and friction, specifically air friction, slowing this down and making it stop. Now, if you were to have something very light with a lot of surface area, it would really be affected by air friction. You wouldn't be able to throw it very far at all, no matter how hard you tried. So there you go. Newton's first law, an object in motion tends to stay in motion unless it's affected by an external force, such as friction, like air friction. So there you go.
Sarah and I have recorded a lot of results on our ramp by raising it till we started to slide.
Here we go.
Now we've decided to raise the ramp to the highest point and see how far we can go using some low friction things, like a wheeled cart.
I've made a double bike cart.
Wheels are great for moving. They have rolling friction,
Ready?
which is different from sliding friction.
What happened?
You went through all those boxes back there.
That was it. We went really far. Total fun. Let's try something else.
So what are we gonna do next?
Now we're gonna do the frictionless this thing that we have at Science Max headquarters, a hover disc.
Oh my gosh, that's so cool. Where did you get it?
Built it, season 1.
Amazing.
As you may remember from that episode, a hover disc uses air to greatly reduce the friction with the ground.
Here we go.
So what would a hover disc do on a ramp?
Right.
Only one way to find out.
Whoa! That was amazing.
That was awesome.
So let's recap. Friction is when two surfaces rub against each other. You can have a very small amount of friction or a very large amount, depending on the materials. And using science to reduce friction results in the best sledding experiences.
Nicely done. Science Max, experiments at large. Your turn?
My turn? Yeah, let's do it.
So take those, and I'll get this, and then I'll give you the helmet. And then we gotta rebuilding the boxes is like the hardest part of this whole situation. But
Today, it's all about opposites. Things that float and things that, don't. Water and gravity.
gravity.
What goes up doesn't have to come down. Unless it's built, poorly. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil. And I am Opposite Phil. Opposite Phil. That's right. Blue lab coat, yellow shirt, evil mustache. I see. Anyway, we're looking at opposing forces today. That's forces that make things go down and forces that make things go up. Right, things with more density and things with less density. Gravity and the opposite, which is anti-gravity. Anti-gravity isn't really a thing. Well, I have to do the opposite. Right. Buoyancy. And buoyancy's opposite, which is girlancy. No, girlancy is not the opposite of buoyancy. You're not helping. Right, not helping. Opposite. Haha. Hello. Goodbye. Today we're going to be making a gravity-powered boat. Ta-da! It's pretty easy to make. You just put water in the top here. Gravity of the water pushes it out the straw, and the boat goes forward. And it's super easy to make. You only need 4 things.
A piece of styrofoam, a plastic cup, craft stick, and a straw. And the tools you'll need, a pen, a craft knife, and the help of an adult, and science glue.
Which is the same as regular glue, except I only use this glue for science. You take your styrofoam and you cut it into a boat shape. That requires the knife and the help of the adult. Then take your cup and draw the circle that your cup will sit in. And then you want to put 2 slashes with your craft knife in there. Again, get the help of an adult if you need it. And then start carving out the styrofoam with your finger and make a nice little indent just like this for your cup to fit in. See? And then it fits in nice and snug. So then what you want to do is you want to make a hole in the cup. You can use a pencil. And the hole has to be just big enough for the straw to fit in. First, you want to take the straw and dig up in this direction so that it will be a nice angle for the water to come out, and then you want to get the straw back up into the cup like that, and then glue it so that it is not going to leak any water. And then in the final step, and this is your choice, you don't have to do this, but you can use your craft stick and you can make a rudder, or if you want, you can make a whole keel, which goes just like that, and it is right in the middle of the boat, and this helps the boat go straight, because sometimes the straw goes off to the side one way or the other. Okay, water-powered boat. Actually, it's a water and gravity-powered boat. You see, what you do is you fill up the cup with water, and the gravity of the water in the cup pushes it out the straw, and the boat goes forward. And this is what it looks like in the water. You fill up the cup, and the gravity pushes the water out that way. The buoyancy of the boat keeps it afloat, and good old Newton's third law, for every action, there's an equal and opposite reaction. The water going out the straw this way pushes the boat that way, and it works pretty well. Whoa, if it's going straight. That's why we have the keel. Okay, so gravity-powered boat. Time to max it out. But first, I need an expert to help me. Oh, of course, Michaela from the Ontario Science Center. Perfect. All right. And let's go. No! I stopped myself. I didn't get wet. Now I'm just gonna get it. No! Oh. Hey, Because I need your help maxing out this. The water gravity boat. It's pretty awesome. And what you do is you put the water in the boat, and then it does this, and it propels itself along. So we're gonna max it out and make it super awesome. So what do you want to do that?
Oh, man. Well, what if we just think about making everything bigger?
Okay.
Right? Like, first we're gonna need a bigger container.
Okay, well, that's a good idea. Tell you what, I got my waterproof portal ordering device. So I'll order some sort of a bin?
Yeah,
Like a big
yeah.
plastic bin. Okay, hold on.
That'd be-
Hold on. Here it comes. Oh, there it is. Okay, so a big plastic bin.
Yeah, and then, you see this straw here? What if we had something like that, except bigger,
Like a pipe of some sort?
yeah, like a big pipe.
One pipe coming up.
I need to get myself one of those.
Yeah, but it doesn't always work, so. Oh, here it is.
Wow.
So, bin is the cup,
Yeah,
pipe is the straw.
yeah.
So now all we need is the boat.
Yeah, the platform itself. I think we need something that's gonna be really stable because we're gonna have a lot of weight this time.
How about like a surfboard or one of those stand-up paddle boards?
Hey, that's a good idea.
Yeah, okay, check this out. Uh-oh,
Oh no,
water stopping.
that doesn't look good.
I think it might have gotten stuck.
Oh,
We'll have to go get it. Because the water is still running and that might overflow,
man,
so.
it's stuck somewhere.
Buoyancy is the tendency for things to float. Things like this balloon, or this ball in water. But it doesn't float on its own. The helium is less dense than the air molecules around it, and they fall past the balloon and push it up. The ball is less dense than the water around it. So the water molecules flow around the ball and push it up. This happens because water is a fluid. The particles flow around each other. This works because air is a fluid. And I know what you're thinking. You're thinking, Phil, air isn't a fluid, but it is. Usually we think of fluid as meaning a liquid, but in this case, fluid means anything where the particles can flow around each other, and that includes air. But you know what? It's hard to see the particles in water. Same thing with air. I can say it, but it's really hard to see it. Now this is sand, and it behaves like a fluid too. Well, sort of. Check it out. Look, it's made of a whole bunch of very fine particles, and it takes the shape of its container. But watch this. I put a ball in the sand, and it doesn't float. Now, the ball is less dense than the sand, but it doesn't float because the particles of sand have a little bit too much friction right now. But watch as we move them around and reduce the friction by adding some air. Now, the sand is behaving like a fluid, and the ball floats. Let's see what else floats on sand. How about this pumpkin? Yup, that floats. How about this block of wood? Yep, that floats too. How about this styrofoam ball? Yeah, that definitely floats. Look at that. The sand is a fluid right now because all of the little particles of sand are moving around. But watch this. If I turn off the air, everything freezes in place. Nothing floats anymore because the sand is no longer behaving like a fluid. So there you go, buoyancy. It all depends on the density of the thing and the fluid it's surrounded by. Huh? Science.
Michaela and I are maxing out our gravity-powered boat. We had a bunch of maxed out materials. We just needed to get our surfboard.
So we got our giant bin,
We got a giant tube. Water's gonna come out of this end.
and we've got a valve here, which means we can fill the bucket, and then we can turn on the valve and see what happens. So, whoa!
Hey.
Okay, you ready?
Yeah.
Now we're gonna turn on the valve, and that means now the water is flowing through.
Ooh,
Hey, it's working.
not bad.
Right on. Whoa, look at that. This thing is really working.
Yeah, it's taking off now.
So, okay, this is good. It's going about walking speed. Now that it's working, how do we max it out?
Our fuel here is the water, so
Yeah.
what if we just had even more water?
And it doesn't last long, does it?
Yeah.
Maxing out our boat even more is easy. A bigger bin for more water, and a wider pipe to move more water for more thrust.
Okay, so a bigger bin
Yeah.
is a lot harder to fill because it's hard to get to the top of it.
Well, you're working against gravity, so it's gonna work for us.
I can really appreciate the amount of water that we're putting into this. That's 4 buckets full.
Wow.
This is 5 buckets.
We open up the valve and it starts to go.
Yep,
Working.
it is working. Look at all the
Wow.
awesome
Check
bubbles.
that out.
Okay,
That works really well.
it really, yeah, it's definitely
Wow.
faster than the other one. I think it's the larger pipe, and we need more water because it doesn't last very long.
Check it out. It looks like it's going even faster now that we've lost a bit of the water.
Less weight.
Yeah.
This is working great, so now how do we make it even better?
Okay, well, the only force working with us right now is gravity, right? Of
Right.
the water coming out. What if we add in an extra force?
And we could squish the water down to go out faster. Okay, watery high five. Okay, we gotta get it's way over here. Come on, we gotta get it. I want to move the water from this container to this container. Now, I could just pour it, but what if it's too heavy? It's too heavy! Help me, science! Well, science to the rescue with this! A clear plastic tube! Ooh, science-y. Okay, watch this. I'm gonna make a siphon, and it's pretty complicated, so follow along. Are you ready? I stick one end in here, and one end in here! Whoa! Yeah, I know, it's not working yet, but that's because we haven't added the science. First, we need to add a little bit of suction and suck the water through the hose like a straw. It has to go over the highest point. Watch this. And there we go. Look, the water is going up. I can even make the water go up even more, and it still works. But why does the water go up? Water doesn't like to go up, right? Well, the reason why is because there's more water going down than there is going up. So that creates suction on this end, and the gravity of this water pulls that water up. So gravity is doing all the work for us. And that is a siphon. Huh? So now let's max it out. This is the same container of water, but now it's colored slightly blue so you can see it go all the way up through this hose. The only really hard part about this is sucking the water all the way up to there. Okay, here we go. I got it working. Now, the reason why it's working is because there's just a bit more water on this side of the tube than there is on this side of the tube.
With a siphon, it doesn't matter how far you go up, as long as the water on one side is lower than the other.
Science. You know about helium balloons, right? Helium is a harmless gas that is less dense than air, which is why helium floats.
If I was to breathe some helium, my voice sounds higher because helium is less dense than normal air, so my vocal cords vibrate faster. Ah!
But have you ever wondered, is there a gas that's more dense than air? There is.
It's called sulfur hexafluoride, and it's much more dense than air. So if I was to breathe some, my vocal cords would vibrate slower, making my voice lower. Ha 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 ha!
This container is full of sulfur hexafluoride. Ooh, I know, it's invisible, you can't see anything. But watch as I blow some bubbles. The bubbles are floating on top of that layer of sulfur hexafluoride.
The bubbles float because they're full of regular air, which is less dense than the sulfur hexafluoride.
In fact, a balloon will float on this as well. The balloon floats lower because the weight of the latex also drags it down a bit. But the bubbles and the balloons are floating on a sea of sulfur hexafluoride. And it is like a sea because it's a fluid just like water, but it's more dense than regular air.
Science! It's awesome!
Michaela and I are maxing out our gravity-powered boat. It was already working well, but now our idea is to try squishing out the water so it gives the boat more thrust. We just had to come up with a brilliant idea how to do that.
Garbage bag! Garbage bag! Yeah, garbage bag! Okay, maybe we should explain the garbage bag. Okay, so the garbage bag is attached to the pipe at the back end. There's a hole in the garbage bag. Well, we fill the garbage bag with water. Then we tie the garbage bag tight. Tie the knot so the air doesn't get it. Now that we've got that, we use bowling balls! And we put the bowling balls on top of the garbage bag, and this will, whoa, squish the water out.
Really is pushing on that bag.
Okay, ready? Okay, let's see.
Hey, it's moving.
Our bowling balls were squishing the water out, but the boat didn't seem to be moving much faster.
I think the bowling balls made the whole thing too heavy.
What if we raise the bin up?
If it's higher up, then there would be more force due to gravity.
Yeah, so we have the bin on like stilts or something,
Oh my God.
and then it has to fall further, and then maybe the water's going faster.
I love that idea.
Okay, good.
Yeah, let's try it.
So what we need to do is get
Wait,
this.
no.
Oh, I thought this is the shallow
No,
pool.
yeah, no, that's
that
over
one's
there.
that's that
yeah,
one. Yeah.
not here.
Max Historica. Long, long ago, in the time of ancient Greece, there lived a genius named Archimedes. One day he was in the tub and he noticed something.
Oh, hello. Look at that. When I get into the tub, the water level goes up, and when I get out of the tub, the water level goes down. Ha ha! Eureka!
I, don't get it.
Well, I can calculate how much volume something takes up by how much water it displaces.
Yep, still not with you.
Now, I'll give you an example. How much water would be displaced, pushed aside, if I put this ball in the water?
It's light, so not much.
Ah, it doesn't matter how heavy it is. It only matters how much space it takes up. Watch. Ah, you see? The same volume, huh?
I think I see.
How much water will be displaced when I put this bowling ball in?
More because it's heavier.
Ah, nope. It doesn't matter how heavy it is. It only matters how much space it takes up. Watch.
Oh.
You see? A simple and easy way to measure something's volume.
Archimedes, one of the greatest and cleanest scientists in history. Join us next time for more Max Historica. The metric system in 60 seconds.
The metric system is a way of measuring things. Water boils at 100 degrees Celsius, a kilometer is 1,000 meters, but few people realize just how interconnected the metric system is. First of all, it breaks down to a base 10 system. Everything is 10, 100, or 1,000 of everything else, and it's all based on water. This is exactly 1 liter of water. It weighs exactly 1 kilogram. It fits into a cube 10 centimeters on each side. It boils at 100 degrees Celsius and freezes at 0. And this happy little fellow is 1 milliliter. It fits into a cube 1 centimeter on every side. It weighs exactly 1 gram, and the amount of energy required to raise this 1 degree Celsius is 1 calorie. The metric system, everything interconnected and all based on water. Ha! Oh. Uh-oh.
Michaela and I are experimenting on our maxed out gravity-powered boat. Trying to squish the water out with bowling balls added too much weight for it to make much of a difference. So now we've raised our tote higher up, which means the water will have farther to fall and be going faster when it comes out.
And I got a totally awesome name for our boat.
Tell me, what's up?
Totes McBoats.
That's a totally awesome name!
Totes McBoats? Yes! Okay, so are we ready to fire up Totes McBoats?
That's right, yep.
Okay, I'm gonna turn on the valve. Okay, ready? And let go. Totes McBoats!
What we hadn't considered is that much weight that high up would be tippy.
Totes McBoats no longer afloat.
We needed a way to solve the tipping problem first.
You know what we need to do?
What?
We need to build an outrigger.
All right, so check it out. This time we have an outrigger, which means our boat's gonna be a whole lot more stable. It's not gonna fall that way because this thing is floating, and it's not gonna fall this way because it has a lot of mass as well. Think we're almost ready, eh, Phil?
Yeah. Okay, are you ready?
Ready?
Okay, let's do it. Turn on the valve.
Here we go.
Go, Totes McBoats. Oh, yeah.
Hey.
Yes.
Whoa.
Yes.
Yeah.
Totes McBoats. Uh-oh, the outrigger's pulling it to the side. Whoa. in this way. Good! It goes really fast.
Our gravity-powered water boat worked great. The water ran down from high up, giving it more speed due to gravity, but no more mass than before. And our outrigger kept the whole thing from tipping over. Totes McBoats was a success.
Thank you very much, Science Max Experiments at Large, gravity-powered boat, otherwise known as Totes McBoats! Totes, come back, Totes! Come back! Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Whoa. Oh, I better spin the other way. Today, we're gonna be taking a closer look at spinning. Well, all things spinning. Spinning, rolling, rotation in all its forms. And, when things spin, they're subject to a whole bunch of different forces. And some are strong enough to even counteract gravity. So let's get spinning! Whoa. Okay, let's get spinning! We are going to make a gyroscopic whirligig, and it spins, and I don't, which is a good thing. Watch this. You pull the string, and it spins, and it stands on its end.
Why does it stand on its end when it spins? Because of angular momentum, which we'll get to later.
And here's how you can make one of your own.
You will need some craft sticks, string, a small zip tie, a shish kebab skewer, spacers like these wood blocks, and finally some round discs, which you can cut out of plastic or find from parts of broken toys. Now, if you want to research this yourself, look up gyroscopic whirligig.
Get 2 craft sticks and glue them to your wooden blocks just like this, and then do it again.
Space them apart and glue them to crosswise craft sticks, and this will be your launcher.
You put your hand in the small end, and the longer end here is where you put your gyroscopic whirligig. Now let's make that. What you want to do is you want to take a shish kebab skewer or whatever fits the diameter hole of the round things that you're using. I like to use little plastic discs from, these are from remote control mechanisms, but you can use anything you want.
I found that this launcher works best with 4 discs of the same size.
Just like that.
Space them out evenly, glue them down, and cut the skewer even on both sides. Then add your zip tie. Put it right in the middle, tighten it up, and cut off the dangling end. This zip tie just gives you somewhere for the string to hold on when you wind it up. Now for your pull handle. Glue 2 craft sticks and 2 wooden blocks, then 2 more craft sticks on the sides. Then tie a string to the middle, wrap that string around the middle of the whirligig, and
Aha! You have a gyroscopic whirligig, a pull handle, a rope, and your launcher. Now remember, you put your hand in like this, and you fit your gyroscopic whirligig in just like that, and you pull towards you, and it spins! Oh, and that's what we're gonna be doing today, Science Maximites. We're gonna max out a spinning rig, something like this. It's gonna spin bigger, faster, more weight. It's gonna be totally maxed out. So come on. But first I need an expert to help me out. So, let's see here. Wait a minute. Aha! Perfect. Come on, this is gonna be great. Okay, this is it. Hey, Sailita from the Ontario Science Center. I'm really glad you're here. You're gonna help me max out the gyroscopic whirligig.
The what?
Oh, the gyroscopic whirligig. Here, I'll show you. It's this, and it spins, and what works on
Phil, where are your shoes?
I think these are my shoes. They must have changed into flippers in the portal. Weird.
Want to change them?
Yeah, I'll be fine. Anyway, like I was saying, the gyroscopic whirligig is really good. Let's do it here so that I don't have to walk as far.
Can I see it?
Yeah, here it is. Ready? You spin it up, and it spins, and it goes for a while, right?
Because you made it out of 4 discs, it probably spins better because there's more mass.
Oh yeah, because you know what? I actually have an old one. Yeah, I got an old one here with 1 disc, and it does not spin as long as the 4-disc one.
Could we test the 1-disc one out and compare it to the 4-disc one?
You bet, because you know what that is? Science.
Science.
Yeah, that's science. Okay, let's try it. Ready?
Whoa.
Oh. Huh, look at that. The 4-disc ones spin better longer than the 1-disc one because the 4-disc one has more
Mass, therefore more inertia. So when we max it out, we should get something with a lot of mass.
Yeah, more mass.
Wait, I have something. Right. Whoa. Can you give me a hand?
Careful, Phil. I don't want you to fall.
Yeah, well, I don't want to fall either. It's hard to walk in these.
I can imagine. That's why I asked you if you wanted to change your
Nah, we're
shoes.
fine. I'm fine. Okay, check it out. This is what I was going to. Okay, this is what we can make it into our maxed out spinning gyroscopic.
I don't think so.
Why not?
It's just, look at how big the hole is.
Oh, yeah, because we're going to need something to be the axis, huh?
Yeah, we need like a tree to fill that. I don't
Yeah,
think
you're
that's
right.
gonna work.
Too big. Is there anything else wrong with it?
It's also kind of light. It's not that heavy.
More mass, better.
More mass.
Okay, tell you what. Oh, I know. Hold on. I know. Whoa.
Oh, that looks perfect.
Yeah, and then we got this pole.
To go through the center?
We'll go through the center like that.
Awesome.
And then we'll just weld it together, and there you go.
This will be great.
Yeah, high five.
Phil.
Okay, no, wait, sorry, yeah, you got the thing.
High five.
Well, now I got the thing.
Yeah.
All right, I'll get new shoes, and we'll work on our high
Okay.
five. Now it's time for one of my favorite scientific terms, the Magnus effect.
I am Magnus, and behold my effect.
No, the Magnus effect has to do with things that are spinning. Things like these cups. And here's a great little Magnus effect flyer you can make at home. It's super easy. Get 2 styrofoam cups and tape them together at the bottoms using science tape. Then get some elastic bands and make a long one by tying them together. Take your elastic and you wrap it around the cup like this. Then hold the elastic on the bottom, remember, like that, and then let them go. They fly up and out.
The reason why it goes up and stays in the air is because it's spinning, creating moving air over the top. Moving air has lower pressure, which means it's pushed up by the higher pressure underneath.
And that is called the... It's coming. Oh, come on.
Now, the Magnus effect.
Yes. So, let's max it out.
Magnus it out. See how much better that sounds?
No, max it out. Check it out, Magnus Flyer 2.0 stand elastic slingshot. Wrap it around.
Remember, for the Magnus effect to work, your cups need to be spinning this way, the front side rotating up.
Oh, and there you have it, the Magnus effect.
I, Magnus, am now taking over the show. It is now Science Magnus. That is my effect, slightly improving the name of science TV shows. Science Magnus.
Silita and I are maxing out our spinning top. Based on our small version, we decided to make one with as much mass as possible. So we got a 20-kilogram weight and welded it to a metal shaft. Will this work the same way? Well, let's look at the science. Why does a top spin? Well, let's start with Newton's first law, which is an object at rest tends to stay at rest, an object in motion tends to stay in motion. But the in motion has another part. That object also wants to go in a straight line. If you think of a bowling ball rolling along, it would need another force to act upon it to make it change direction. We say that a moving object has momentum. Now, a top doesn't go in a straight line, it spins around, but it still has momentum. It's an object in motion, and even though it's spinning, it still does want to go in a straight line. It's just that that straight line is here. We call this angular momentum. To make a top move this way, or that way, would take an outside force, so it stays upright as long as it has enough momentum. But when it slows down, there's less momentum and it becomes harder to resist external forces, like gravity, which will eventually want to make it topple. Our top has a lot of mass, which means it'll have a lot of angular momentum when it gets spinning. It's just a matter of getting it spinning fast enough.
So should we spin it?
Yeah, let's spin it. Let's see if we can get it to work. Hey, Okay.
Spin.
Oh, we're gonna let go. In 3.
Wait. I can't get it.
1.
Wait.
Okay.
Okay.
Not fast enough. We need something to help us get it spinning faster. Maybe a rope?
A rope, yeah.
Wrap a rope
That
around
was
it,
my
like
idea too, a rope, because the small one uses a rope.
Yes.
Okay.
Okay, I'll go grab a rope.
So, wrapping the rope up.
I'll let you wrap the rope
Okay.
up. I'll get my holder back on top.
Spin it counterclockwise.
We attach the rope and wind it up.
You want to make it super clean. This is some of the best coiled rope I've ever seen. I'm gonna pull the rope. You're gonna hold on to it, but I can't pull really hard because you won't be able to hold it up. Because we don't have to pull hard, we just have to get it going fast.
Yes.
Silita keeps her hand on the block at the top, and I pull.
Ready?
Wait a minute, we'll get all the way. Oh. Whoa!
Spinning a lot better than I thought it would. It's still spinning, but it's wobbling.
Oh, careful.
Oh, there it goes.
It works, but just barely.
It might spin better, it might spin straighter.
Yeah.
If we had it spinning, something help us spin it faster.
Yes, faster with more power.
With more power.
This is a string. You can pull a string, but you can't push a string. Well, you can. You can push a string. You really can. Okay, quit it. Quit it. This little contraption works sort of like a baseball pitching machine, but in miniature. See, there are two motors here, and the wheels spin together to shoot things out this way. Things like this craft stick. Watch this. Whoa! Let's watch that again. Whoa! But now, watch as I put a large loop of string through. What? Pushing string. How does this happen? Hello?
I don't suppose it's the Magnus effect?
No, it's not the Magnus effect.
No, it's all right. I'll be in my lair if you need me.
Okay, right. Bye. Right. Where was I?
I believe you were at, the reason why this works is...
Right. Pushing string. How does this happen? It's all because of inertia. Check it out. The wheels are pushing the string through fast. It's got some weight and it's got some speed, which means it has some inertia. So when it goes this way, it wants to keep going this way. But it goes all the way to the end, and then, because it's a loop, gets sucked back in this way, which means all of this inertia, you can sort of overcome gravity. Pushing string. Science.
Silita and I need to get our maxed out top spinning faster. We tried a rope, but now we're trying a drill. We get a wheel on our drill and use it on the outside of the weight to get it spinning up.
A little faster.
Oh, it's popping now.
A little more.
Push me.
And release. Whoa! It's kind of cool that it wobbles that much and it doesn't hit the ground.
It worked better, but there's always a way to max it out even more.
You know what we need, Silita?
What do we need, Phil?
A maxed out drill. Put it right on the top here and get it spinning very, very fast. Super maxed out gyroscope
Okay.
whirly gig.
Gig.
Is it just the top now?
I don't know. Do you
We
want to
could
be
call it
calling
a gyroscope.
gyroscopic
Well,
whirly
it's
gig?
sort of a toppy, kind of gyroscopy. This is a bike tire. It's pretty light, but I still can't hold it from the end of the pole like this with one hand. Nope. But I can if I get it spinning fast enough. I just use this drill, and then I get... Okay, so this is gonna be awfully hard to do with one person. Oh, this is the perfect opportunity to use the Trevor button. Haha, Trevor button. Hey, Trevor from the Science Max build team. What are you doing?
Maxing this out.
Oh, right on. Can you give me a hand for a second?
Sure.
Awesome. Okay, so you take this drill, and we're gonna get this wheel spinning really fast.
Okay. I don't know if it's,
No, I don't wanna know.
I don't know if I remember to...
No, it's fine. Max it out. We gotta max it out. So, because it's spinning, I can hold this heavy weight in the air.
How is this possible? because the wheel is basically a top. The forces that prevent a top tipping, angular momentum, are still working here. This angular momentum resists a change in direction this way, which is how gravity would want it to tip. Interestingly, these same forces also keep it spinning around me in a circle.
So, I can lift a heavy weight in the air just by spinning it. Awesome max out experiment, Trevor.
Yeah!
What was that?
It's my science confetti high five I just made.
You know what we should do?
What?
We should max it out. Yeah, we can make a giant one and then a whole bunch of confetti in it, and then people like jump up and do more confetti that would come out, right? And then so what would happen is there would be all this Trevor?
Silita and I have maxed out our spinning top. The trick is getting something that heavy to spin really fast. We've tried a rope and a drill, but now we have a maxed out drill.
So more power and more speed, which is perfect for spinning this massive top.
Yes, and perfect for maxing out anything.
We get it spinning and it works great. The top spins for a really long time. In fact, its mass was so large, it started drilling a hole in the concrete floor. We tried it again, but started to notice something.
The drill is smoking quite significantly.
Our drill began to overheat. Why? Good old Newton's first law. An object at rest wants to stay at rest, and an object in motion wants to stay in motion. The more mass we have in motion, the longer it will stay in motion.
This will go forever. Well, not forever,
Well, not
but
forever.
it'll go a really long time because it's got a lot of weight.
But that same mass wants to stay at rest when it's not moving. We have to overcome all that mass wanting to stay at rest to get the top spinning. And even for our maxed out drill, that was a tough job. But once it was spinning, there was only one thing to do. Max it out even more! Silita and I come up with a plan to max out the top by riding it.
You want to ride the top?
Of course I want to ride the
We
top.
can both ride the top. One person's gonna have to drill this, so we'll have to take turns.
Max Historica. This is Leonardo da Vinci, one of the greatest scientific minds the world has ever seen. And this is a wheel. Da Vinci thought to himself, wouldn't it be great to design a wheel that kept spinning forever? So he got to work. Something that keeps spinning forever without stopping is called a perpetual motion machine. And it was an obsession of Da Vinci's. Why, this is great. The bottles tip the water to the outside, making one side of the wheel heavier, which will keep it spinning forever. Except it doesn't work. You see, what Da Vinci doesn't know is that science says a perpetual motion machine is impossible. But of course it wasn't for another 350 years till scientists figured that out. So we can't tell Da Vinci. What? Oh, never mind. Leonardo da Vinci, one of the greatest inventors ever. Even if not all of his inventions worked. Silita and I got our maxed out spinning top to work pretty well. The only thing left to do was to ride it. We attached a large disc and a Lazy Susan. That's a platform that spins around on ball bearings.
Lazy Susan on top,
Lazy Susan.
so that you can ride on it.
Yes, and then we wanted to add this extra bit. Now, why did we want to add this?
We need a little bit more weight on our top.
Okay, so who gets to ride it?
I feel like you should ride it.
I think you might be right.
Because I want to use
Oh,
the drill.
the super awesome maxed out drill. Okay, so let's do it. First thing I should say is do not try this at home. We are trained scientists.
Silita uses the drill to get it spinning while I hold it steady. Then I hold on to our safety line above and carefully rest my weight on the top. It works, but not for long. We take turns trying it out, but it seems we have another part of science working against us. Good old friction. Friction with the air and with the ground is what eventually slows a spinning top down. But our weight on the ball bearings of the Lazy Susan really increases the friction. More friction means the top slows down a lot faster.
That was pretty cool.
It was kind of terrifying, right?
Yeah.
Good old Newton's first law kept the top spinning, angular momentum kept it from falling over, and friction slowed it back down. The forces were always the same, no matter if it was a little top, a maxed out top, or a rideable one.
Yeah! Whoa. There you go. Science Max. Experiments at large. Giant spinning top. That's as large a spinning top as I think you.
I think in the entire world.
Let's do it again. Yeah!